All right, so let me move on to the next topic about swine transformers. I think it was introduced in 21. All right, so I talked about two issues in transformers. One is that, okay, so there's no natural, in vision transformer, natural notion of patches. And the second one is the lack of inductive bias. And we came up with some sort of solutions to tackle those problems. The third issue in the transformer, in vision transformer, is that the model is as good as the resolution of your patches. So because each patch is viewed as an independent element, like, because again, we are using transformer from the language domain, right? In the language domain, you have a word, and that's it, right? So you really don't care about the letters in that word, because the combination of the letters, they form an independent element, and you're good, right? So, okay, maybe like one word may have like different meanings, that's completely fine, right? With respect to the context, but you really don't care about like the combination of the letters in a word. But in images, that may be a different story. You may have a patch, let's say 16 by 16. There may be a lot of things going on in that patch. You may have like a bunch of objects, small objects within one patch. And we are putting everything together in one independent element. Right? So what happens, for example, if you want to solve image segmentation? Image segmentation is a problem where you need to assign segmentation values for each pixel. Right? So you want to solve this problem in the pixel resolution. But now you have 16 by 16 patches. They're all within one group, within one element. So you cannot go higher resolution than 16 by 16. And that is a big problem, especially in the vision domain. All right. So another issue is that the resolution of patches limit the ability of vision transformers on high resolution tasks. For an example, just imagine you have an image. Again, we are looking at 16 by 16 patches, and here you may have like multiple people, multiple objects. Then you won't be able to, for example, detect those individual objects within a patch, because that's not the resolution that you are even looking at your input image. Same, so here detection is going to fail. Segmentation requires understanding images in the pixel resolution level, right? So when you're looking at 16 by 16 patches, your model is not going to be successful in those types of tasks. Okay, so the question is, how can we solve this issue? Right, I'm looking for some ideas. Yes?
Something like sliding window.
But the sliding window, it is not going to solve my problem, right? Because if I'm starting with like 16 by 16 patches, whatever I do after that, because I take a patch, I vectorize it, maybe I embed that using a projection head, and like I can do whatever on top of it. I'm not going to recover the information within that patch for those individual objects or in the pixel resolution. That's not going to help me. One more idea. Yes.
You can slide windows of different sizes in hierarchy.
Don't forget about sliding windows. That's not going to help you. Someone from the back row, like the last two rows. Just want to make sure that you guys also stay awake. Any ideas? If you have a good idea, you get an A+. Yes. You go. Great suggestion. I think you should get an A+. So the idea is that maybe we can look at like different resolutions, right? So maybe start with like higher resolution, and then go towards lower resolution in the later layers. In other words, maybe in the first layer or the first level of applying our transformer, we should go high resolution, right? Because there's no other way around it, right? So if you go 16 by 16 patches, like there's no way to recover the information within that patch. Right? So we should go higher resolution, meaning that we should maybe consider 4 by 4 patches, like much smaller. So what is it? Maybe like 1 by 1 patches, like, you know, pixel. But why we didn't do that? What was the reason that we didn't? What was the intuition behind patches? Right? So why didn't we go with like having individual pixels represented as tokens? Computation issues, right? Because remember, I made this big of a deal about, oh, look at or resolutions of the images, like let's say I have 1080 by 1920, then I'm going to have like more than 20 million tokens if I look at individual pixels, right? And the computation is going to be a big challenge for me. All right, maybe I was wrong, right? Or maybe I was misleading you 15 minutes ago. Maybe we can start with individual pixels, or okay, let's say 4 by 4 like patches, and try to deal with the additional computational overhead within the architecture itself, because there's no other way around it, right? If we start with like bigger patches, we are losing that information. So we have to start with smaller patches. There's no other way. And so let's start with that, and then see where can we do like some savings in terms of the computation, because the only issue is the additional computational overhead, right? So let's just look at our bank accounts and see, what are the, subscriptions that, maybe we'll unsubscribe from Netflix and, HBO Max, and all of these, and try to like only keep the ones that are really important. Okay, so let's do that. All right. So the idea, again, use smaller patches in earlier layers, but try to save computation. All right. So in the paper, they start with 4 by 4 patches. And if you consider RGB images, they have 3 channels, right, for red, green, and blue. So there are also 3 channels. So altogether, how many numbers do you have? 4 times 4 times 3. You get 24 numbers, a vector of 24 numbers. Remember, before, if you're considering 16 by 16 times 3, you get like much bigger vector as your input patch. Again, it's 4 by 4 by 3. So you vectorize it 24. Okay, good, right? So at least now we have a good resolution, 4 by 4. Okay, I'm happy. Okay, so let's look at our spendings. Okay, so what should I do? Should I just use a vector of 24 numbers as an input to my encoder, or can I make some savings here? Come on, guys, with my tone and stuff, the answer is like obvious, right? How can I make some savings here? Do a linear projection, right? Just to shrink it a little bit further, right? I'm, really becoming economical. I just try to reduce my computation as much as possible. So I'm going to do a linear projection. I'm going to map it to only 4 numbers, because I really want to push down my computation, right? Only 4 numbers. So I'll add my positional embeddings. And this is important, right? Because remember, one overhead in terms of the computation is the application of the feed-forward network to individual embeddings of these patches. Like, yeah, obviously we have like way many more patches compared to like the previous case. But if the input is smaller, then these feed-forward networks are going to be like much smaller. So we will save quite a bit of computation by just that reduction from a vector of 24 to a vector of length 4. So it is a good saving. So it is not just dealing with the smaller vectors, because the feed-forward network itself is going to be smaller. That is applied to individual vectors, right? So that's a good saving. So we got rid of our Netflix subscription. HBO is gone. Hulu is gone. All right, so that's good for our feed-forward network. But what about like the next layer? So after adding the positional and embeddings, then we have this cross attention layer, right? Cross attention. And if I have n tokens or n patches, as we discussed previously, the computational complexity is like order n squared, because you're considering every pair, and you're saying that, okay, so what is the probability of having one related to the other one? And you're using that probability to update the embeddings. And the issue is that n is big, right? Because we are looking at smaller patches, or n can be in the order of millions. Then even though like by just projecting to a smaller vector, that's good later on for my feed-forward network, like, because after this, what do we have? We have obviously add and normalize, and then we have the feed-forward, right? Feed-forward that is applied individually. This reduction is good for later on, because we will have smaller vectors. and therefore smaller feed-forward network. So that's good. But again, we have an issue here, right? So we have an issue in the cross attention. Cross attention doesn't care about the size of your vectors, because you still need to look at every pair. How can we deal with this? How can we save some computation here? Yes?
Disregard far.
Say it again?
Disregard patches.
Exactly. Disregard far connections. Absolutely. So, okay, so how often, like, let's say, what is it? So, like, you have a patch here on the top left, and you have a patch here on the bottom right. So when you're computing your attention matrix, you assign some potentially non-zero probability of attention between these two patches. But maybe, like, you know, it's like keeping like a Hulu subscription, because maybe like an episode of one of the series that you have been following will be like out in like 2 years, right? That's not really important. Right? Let's just get rid of it. Let's look at localized attention. And that's the whole idea of a method that they call window-based self-attention. Really intuitive, right? So what is the idea? The idea is you have like some windows, and you can only have non-zero attention within those blocks. That's it. The rest, you don't care. You don't compute the attention probabilities in those blocks. It's a window-based self-attention. And depending on how many, what is the size of your window, obviously, if it is like the whole, it covers everything, you'll get n squared, right? But you have it constant, so you don't have n squared. So you get something linear times a number that depends on the size of the window. So you save quite a bit. M is like, roughly speaking, the number of tokens within that window. That's it, right? So you save from the computation in the cross attention layer. Add and normalize doesn't cost anything. It's just a normalization. Feed forward can be done effectively because the size of your vectors are much smaller. And then add and normalize, it is okay. So the output will be, again, vectors of length 4, the encoded versions of your input vectors. Let me pause and see if there are questions so far. Yes?
These windows, are they designed to incorporate 2D information, or are they just chunks of your linear?
2D information, right? Because you want your patches that are nearby, that's a very good question, in the 2D to be able to talk to each other. Absolutely. So we are using a little bit more 2D information by designing those windows. Absolutely, yes. Yes. Self. Just want to make sure you are awake. Oh, self-attention. There you go. Come on, man. All right. No, it's good. It's all good. All right. Yes.
So just because we chose this design, can there be an adversarial attack which could?
There's always adversarial attack, but let's not worry about that for now. We'll talk about it in another lecture. One more, Mehdad.
Why aren't we using linear attention as we discussed before instead of this? Because it doesn't have like localization bias, but then you can just use more data, as you said.
Yeah, maybe you can use that, but the issue of the linear attention that I covered the last in the last lecture was that it is linear in n, but it has some additional complexity depending on the kernel size.
Vectors are small layers, so that wouldn't be.
Yeah, perhaps that can be used, but that's not the method that is used in the paper. I'm not saying this is the only way of doing it, but it's one way of saving computation. One advantage of this approach that I like is that we are using more 2D information. We are kind of trying to make vision transformer look like a convolution network, right? So by having these types of constraints based on the geometry of the image, so we are going towards that. So that's why I also personally like this approach. All right, so let me move on. So this is one layer. Right? So you have, at this point, several options. You can apply the same layer over and over again and try to solve it. What would be an issue about that approach? Yes? Good. So if I apply exactly the same layer, the issue is that like these windows, let's say it is kind of arbitrary, right? So you're saying that, okay, so these, like this part of the image talk to each other, then the other part of the image talk to each other. And there is no crosstalk between those two parts, which may be important. Okay. How can I solve this problem? Change your location of the windows, right? Maybe at the beginning you had let's say you're masking, let's say this is one window and this is the other one, and for the next layer you can, I don't know, like have this one as your window. You can shift it. You can have other ways of partitioning your image to create your attention constraints, right? Across different layers. Fantastic, good. So that is in fact called shifted window-based attention, because in different layers they don't use a fixed location for these attention constraints, so they shuffle around the windows and the masks. So that's why it is called shifted. Okay, so that solves one of the issues. Is there another issue? Let's say I have another windows for the next layer. Should I just apply a similar architecture on top of what I have in my next layer? What would be a potential disadvantage of that, and how can I resolve that issue? Yes?
Running something with the same window size would be computationally expensive, so we can increase the resolution.
Yeah, okay. Yeah, maybe computationally, but that's a part of a problem, right? Because I made a lot of savings for one layer. Maybe for one layer I can tolerate it, but if I apply the same layer like 6 times, maybe the sum of the additional computation is going to be expensive. But that's not like a big of a deal, right? So let's say I'll buy another GPU and I'll resolve that problem. Right? So one other potential issue is that, okay, so in convolution networks, so when you're going deeper and deeper in our model, the features, they become more and more meaningful. So the earlier layers, maybe you are looking at, okay, some very specific patterns. There is an edge here. there are other types of more local information. But when you're going to like more and more deeper and deeper layers, and you look at like, for example, the visualizations, the saliency maps corresponding to those features, you say, okay, so maybe like this particular deep feature, it kind of highlights the whole head of, let's say, an animal, or it highlights, a particular object. So it becomes meaningful. The meaningful pixels, they kind of get clustered in the feature space. But if I keep the same resolution, like my patches, small patches that I considered, and I projected them to like a vector of length 4, then I never get them to be merged with each other. So that is like the second issue. And the way that the issue is being dealt with is via a merging layer between two layers of encoders. Merging layer. So the merging layer, it just merges patches. That's it. So and it merges patches based on, again, the 2D information. And so remember, each of these tokens that we have, they correspond to a patch, like 4x4 patch on the original image. Let's say this corresponds to this patch, and let's assume this particular token corresponds to the other patch. So the merging layer, it looks at 4 adjacent patches, and it merges their corresponding vectors. But the 2D information is being used here. So that's the important part. It's another place that we are using the 2D information, because obviously we want to make sure the patches that are merged with each other, they're nearby in the image. So therefore, you have a vectors, 4 vectors of length 4. After merging, you will have a vector of length 16, right, or 4 times c. And you're going to have fewer tokens to worry about. And that can provide an additional saving in terms of the computation in the later layers. So therefore, maybe for the other layers, maybe we don't have to unsubscribe from all of the accounts that we have. Maybe we can keep one of them. Maybe we can keep, what's your favorite streaming service? HBO Max. Okay, so big fan of Game of Thrones, then we'll keep HBO Max, even though it is a little bit expensive, but that's fine. Okay. So what do I mean by that? In my projection, I'm going to not project them to 4 numbers, I'm going to project them to 8 numbers. I'll keep it a little bit longer in terms of the representation. Eight numbers, but I have fewer patches, and that's it. And then you go to the next layer. The rest is the same. That's it, right? So it is kind of trying to mimic the way that we were thinking about designing convolution networks by looking at bigger and bigger filters, right? Basically looking at patches that are bigger in the image. It is basically doing the same thing by doing the merging, and you follow it, but in the next layer, the attention windows are going to be also shifted, so different tokens and different parts of the image can talk to each other. And then you push forward, you can go up until any point that you like. Maybe you can stop in the next layer. You'll have a bunch of vectors. You can merge them. You can use that in classification, or you go as far as just obtaining one vector representation for the entire image. That's up to you. All right, so that is it. That's all I had to say with respect to vision transformers and transformers. I'll pause here and see if there are any questions before moving on to the next topic. Yes. I'm sure it works very well. You can look at the numbers in the table. Yes.
I may have missed it, but what is the actual merging operation?
Just like you have 4 vectors, just concatenate. Yes.
What exactly does the window-based self-attention layer actually do?
Okay, so maybe I didn't explain it well. Okay, imagine this is your image, right? And you have patches, right? You have small patches. Okay. So in the original attention, every patch can have non-zero attention probability with respect to another patch, right? So this patch and this patch, they can have, remember the P matrix that we had, like n by n? So n is the number of patches that you have, or the number of tokens that you have. They can have non-zero probability. Expensive, right? Because you need to fill in like an n squared numbers in this matrix. So instead, we are going to, let's say, all right, so only these 3 patches talk to each other. Then these 3 patches talk to each other. Right, so I need more colors, but we have more options. And these 3 patches, they talk to each other, so on and so forth, right? So I'm basically saving a lot from my computation because I don't need to compute the attention between these 2 patches. I can constrain my computation to these local windows. And in the next layer, I'll shift them around, right? Because now I want to make sure that, all right, so maybe these 2 patches, they should have talked to each other. Right? So I'll just shift around and I'll have another design for my my windows. That's why we call it shifted window-based self-attention. And you can look at the paper. They have tried some interesting choices for different constraints that they have on their attention in different layers. Okay. Yes. I'm not sure. I think this is bigger. that would be my guess. But you can look at the numbers. And resonance, they come in different sizes, right? So resonance 80, resonance 50. I'm not quite sure about their parameter counts. Maybe one more, yes?
Going back to the more data version of the VIP, like, wouldn't you expect the like model with dense layer to perform maybe even better when you have that much data?
Dense layer.
Yeah, because like how I'm saying is like you are injecting lesser inductive bias, and given that
Like a fully connected?
Yeah, and if you have like
maybe
data number of samples is not an issue, you would you would want a model with more parameters, and essentially that would.
Yeah, I highly doubt it because you're like.
I'm asking your opinion.
Yeah, maybe like you see some gains when you have like billions or trillions of samples, but I highly doubt. So in my opinion, it is always better to impose like some biases, some inductive biases, some constraints that we think that we should have in the model itself, rather than just depending on the scaling of the data. So that's my personal opinion, but I may be wrong. And many of the current models, they only depend on scaling of the data, and they work very well. Under some conditions, they have their own issues. But solving those issues may actually require thinking about adding some of those constraints to the model itself.